Hi there Year 12s and welcome to the first video for the year. Guys, the purpose of this video is to recap the periodic trends for electronegativity, atomic radius and ionisation energy. And I'm going to do that by recapping a couple of key terms that hopefully you guys should all know by now. Whenever you're discussing periodic table trends, then it's really important to bear in mind three things basically, and that is nuclear charge, which is the number of protons in the nucleus. And obviously the nuclear charge is going to be overall positive because protons have a positive charge. We also then need to take into consideration the effect of shielding. Now basically, to recap, what that means, guys, is that the outer electrons, so there's those electrons further away from the nucleus, so if we draw a nucleus here, these electrons out here are shielded from the positive nucleus by those electrons on the inside. So that's another concept that you need to be familiar with. And all of these things culminate in what we call the core charge or the effective nuclear charge. And the mathematical way of saying what the core charge is the number of protons minus the number of inner electrons. So that is all of the electrons in the innermost shells. So they are the three kind of things that you guys need to be very familiar with. Now, to summarize what we pretty much already know in terms of our periodic trend, whenever you're discussing periodic trends, guys, you're going to be looking at a trend across a period or down a group. So if we concentrate on across a period, then we can draw a big long arrow like this, and the ionisation energy, IE, and the electronegativity of any element will increase as you move across a period. Atomic radius, on the other hand, will decrease as you move across the period. If you are concentrating on what happens when you look down a group, then again, ionisation energy and ionisation energy share the same relationship. So IE and electronegativity, and they both decrease as you move down a group. Atomic radius, on the other hand, shares the opposite relationship. Atomic radius will increase as you move down a group. So that pretty much summarizes, guys, what it is that we already know. Now let's look at how we can explain those trends. So if we concentrate firstly on ionisation energy, it is the energy required to remove an outermost electron in the gaseous phase. So you guys need to remember what the definition for ionisation energy is. Now it increases across a period. So this is my increases across a period. Because core charge increases as you move across a period. So if I put the periodic table diagram up again, okay, you guys can see that as you move from lithium here, right, there we go, we can circle lithium. It's got 3 protons here, so it's nuclear charge is 3, right? And every time that you move across, you're adding a proton. But the number of electrons in the innermost shell, like that shell number remains the same as you progress across a period. So effectively, you are increasing core charge with every step across a period. An increase in core charge means that the electrons are held tightly. And therefore, they require more energy to remove them. So their ionisation energy increases as you move across a period. As you move down a group, guys, it's important that you observe this understanding, and that is that with every movement down, you add an extra energy level. So you add an extra one here, an extra one here, an extra one here. As that happens, guys, an increase in the number of energy levels means that the electrons are further away from the nucleus. Further from nucleus. And it becomes basically a distance thing then, Year 12s, and that is that the electrons get further away. So obviously, as you add energy levels, as I'm demonstrating here, the more you add, the further away they get. So it's harder for this positive nucleus to exert its attraction on these electrons out here than it is for it to exert its attraction on these inner electrons. So that's how you explain the phenomena for ionisation energy. Guys, ionisation energy and electronegativity are basically follow the same relationship. So let's take a look at electronegativity. Guys, electronegativity is a measure of one atom's ability to attract electrons. Ability to attract electrons. And they're measured in Paulings, which is after the scientist or the chemist who discovered what it actually means for something to be electronegative. Now, if we consider what happens to electronegativity, fluorine is the most electronegative substance on the periodic table, and its rating is nearly 4. So 4 is the highest number that an atom can have for electronegativity. Guys, the reason why electronegativity increases as you progress across a period is pretty much for the same reason that ionisation energy increases, and that is that core charge increases as you progress because the number of protons increases, but the number of energy levels for electrons stays the same. By the time you get to fluorine, it's got a massive core charge, and therefore it has a greater ability to attract one's electrons because the positive core charge here has got a great affinity for the negative electrons from another atom. The reason why electronegativity decreases down a group is for exactly the same reason that atomic radius decreases down a group. And that is because, the reason why ionisation energy decreases down a group, excuse me. And that's because, guys, you're adding energy levels with every step you take down a group. Those extra energy levels means that the atoms become larger, and therefore it's harder when you've got, say, 4 energy levels. It's harder to attract electrons here because they're further away from the nucleus, and that core charge diminishes in its ability to be able to attract anything. And then, guys, the last trend that we need to be aware of is that for atomic radius. Atomic radius basically has the opposite relationship to ionisation energy and electronegativity. So guys, atomic radius is basically a measure of how big an atom is from the central nucleus to the outermost shell, like that. So from here to here. And basically atomic radius, as you move across a period, atomic radius actually decreases. So across a period, atomic radius decreases. For the same reason that ionisation energy and electronegativity increase, and that is core charge increases as you move across. So you're adding protons all the time, but the electrons are staying in the same shell. If you increase the core charge, then you increase how many positive protons you've got acting on this atom. And therefore, it pulls in the electrons more tightly as you increase positive charge. So fluorine is going to have a smaller atomic radius than boron, for example. As you move down a group, it's pretty self-explanatory. So down a group, there is an increase in atomic radius, and that is because as you progress down a group, you're actually adding an additional energy level every time. Clearly, if you start here with hydrogen, you've got 1 energy level. Here with lithium, you've got 2. Here with sodium 3, potassium 4, rubidium 5. So 1, 2, 3. And if we pretend that's our nucleus, with every addition of an energy level, you're getting progressively further away from your nucleus. So guys, that's pretty much our periodic trends in a nutshell. Probably in closing, I would like you to remember a couple of key points, and that is basically core charge is used to describe any trend for looking at across the period, and the increase or addition, just pretend that's an O, or addition of energy levels explains any trend when you're talking about down a group. So it's important to understand the distinction, guys, that core charge doesn't actually have much effect on the explanation of the trends for down a group. Okay, it is the addition of these energy levels that plays the major role. So it's important to get that right. So guys, that's pretty much periodic trends complete. And I think our next installment will probably be on the shape of molecules and how we can use our understanding of our lone pairs and bonding pairs to try and guess what the shapes of different covalent molecules will be. So until then, happy study.